Awesome. Hello, everyone. My name is Hector. This is Berta, and this is Julian. And we're going to be presenting to you the work that we've been doing at Clemex to make automated image analysis simpler with AI. So a little bit of what we'll be talking about today. First, we'll talk about the issues with traditional methods in metallography and why they fail or why they're cumbersome. We'll talk about how deep learning is slowly being adopted in the field of metallography. And then we'll ask ourselves, is deep learning actually relevant to material science, and specifically the field of metallography? And we'll talk about some real-world scenarios in which we at Clemex are applying deep learning. So first, we'll talk about BrainSeg, which is a product. It's an algorithm that we're developing for universal grain segmentation, even in the presence of common deformations such as twinning or compression lines. And then we'll talk about Clemex Studio, which is a no-code cloud-based tool in which you can upload your images, partially annotate them, and then we can create deep learning models based on that. So, as we all know, one of the holy grails of material science is to determine the relationships between process, property, and structure. Usually the first step is to create some kind of segmentation of your image into the relevant microstructures. Usually it tends to be very hard to do these segmentations because it's very complicated images. They have a lot of patterns. You cannot just apply a threshold to these. We know that these traditional methods are very tedious with several manual steps. So in processing, morphological operations, you name it. We know that these methods can be biased. So here on this image, the authors of this paper asked different researchers to segment different images separately. And as you can see, different researchers arrived to different segmentations. They tend to be non-reproducible because different people will segment images differently. They tend to be time-consuming. They are sensitive to operator. So, for example, on this second example that we have here, these are optical microscopic images of aluminum casting oils. The authors of this paper asked 3 labs. Each of these labs is presented in a different color in the image. And as you can see, they provided very different measurements to these aluminum templates. Finally, these algorithms, these traditional methods tend to be non-generalizable in the sense that, let's say that you find a threshold that works perfectly for a particular data set, you wouldn't be able to use that threshold for other data sets. So it's not a solution that can work right off the bat. We believe that deep learning can overcome these issues by providing a separate avenue of segmenting the images. We can tell you anecdotally that a lot of our clients are a little bit reluctant to use deep learning. On one hand, because a lot of these traditional methods will get them results in 60–70% of the cases, so they're not really interested in exploring other avenues, or they just don't know what this technology can do for them. So as a proxy to demonstrate the development of deep learning in metallography versus other fields, we did a Google search with the words deep learning and metallography, and we got 12K results versus a field that has more widely adopted deep learning, such as medical imaging, where we get 2.5 million results. And some of the interesting things that the medical imaging friends are doing is integrating different kind of information in deep learning to segment chest radiographies. And they're also using CNN-based deep learning to identify different characteristics, such as hemorrhages or tumors in CT scans, in brain CT scans. So at the end of the day, why is this important? We at Clemex believe that deep learning can simplify image analysis by reducing the time and resources allocated to microstructure segmentation. So what we need and what we believe deep learning can bring to the table is a solution that is validated, fast enough, reproducible so that we can have the same results every time that we run the algorithm with the same input, traceable such that we can explain how the model was created, where the data came from, provide traceability, and finally, a solution that's robust to common variations such as data acquisition, lighting, operator, microscope version, all of this. But one of the things that we find commonly with our partners is, well, deep learning, we need a lot of data. These are very data hungry models. So what I propose is that the avenue to generate more widespread adoption of deep learning is through foundational models. So foundational models are models that are trained on broad data. Broad data here means just the sheer quantity of the data or multimodal data that can be adapted to a wide range of downstream tasks. So some of these models, some of the most popular models these days are GPT from OpenAI, Segment Anything or Llama from Meta, YOLO, all of these models that were trained on big data sets that then can be fine-tuned for downstream applications. So this transfer learning, this fine-tuning is what helps us overcome the necessity of getting huge amounts of data. So then we can create models for niche applications where the niche application is so niche that we cannot justify the investment of getting such large amounts of data. For the case of microscopy and image segmentation, we will talk a little bit about NASA's MicroNet. So in case some of you are not familiar with it, MicroNet is a data set created by NASA akin to ImageNet. So it's a data set of different optical microscopy images. And what they did was they trained several encoder models, such as Inception, Exception, MobileNet, EfficientNet. And then they trained these classifiers, and now these encoders can be used as backbones for different models, such as image segmentation, instant segmentation. And these weights are freely provided.
Okay, so just like a quickly overview, as I mentioned, we are like here presenting the importance of having foundational models in this segmentation. So just an overview, semantic segmentation is that you have an image and you put image to your model, and then each of the pixels in that image is going to be labeled according to the classes that you define. In this case, we define two classes, grain boundary, and inclusion. Grain is going to be black, grain boundary is blue, and grain inclusion is going to be red. Okay. One more time. Thank you. Okay. So the goal here is to have a universal grain segmentation. So it's a model that will automatically segment any molecular grain micrography, even in the presence of training, scratches, if the sample was like pre-prepared, so you have a over etching, if there have illumination variations or other informations. So for example, here we have an image. Here you can see like the twin formations, and you can also see that there is like a big shade of grays in the image. So if we apply a threshold, doesn't matter what threshold we apply, we know that for sure we're going to obtain like the grain boundaries that are new. These are the grain. But if we use a foundational model like GrainSet, the one that we're proposing here, we can obtain a segmentation mask that makes more sense and that really can mark all the grain boundaries properly. So GrainSet is a model, it's a deep learning model to do semantic segmentation. As Hector explained, you can have like different pieces for the decoder and the encoder part. For the decoder, we can have a unit plus. For the encoder, we can have an exception, a MobileNet, a ResNet, a BDD. And we use for the tiling because we have like sometimes we have big images from micrographies. We use a tiling procedure that we got from this paper in 2021 that aims to have like a perfect segmentation on a unit. We also have some uninformed loss. So we have a weighted percentropy, categorical percentropy, and we added some terms to have a custom penalization to have a better segmentation of the grain boundaries. We also apply some pre-processing to get grain boundaries that are thinner, the output maps, and we also try different amounts of optimizers. Now, we also add some data augmentation to this model. At the beginning, we have to be honest, like we just apply some random, not random, but we chose some of the augmentation, data augmentation that are in this Python library. But then we realized that we really need to have some domain-informed data augmentation. So then we went with an expert in metallurgy that we have at Clemex. And with her help, we choose like what are the proper augmentations or what are the variations that we can see in the real world of micrographies. So she suggested to, for example, sometimes the same sample in different microscopes can have different colors. So we now are using a color jitter to simulate that, or like random brightness, random contrast, like many others. Now, a cautionary tale from what we learned here is that sometimes labeling this data can get super, super expensive. So in order to do data labeling more affordable, we propose two different approaches. One is active learning. So at the beginning, we were just like getting the data, passing it through the trained model, and then see what else is like gonna be necessary for our model to make it better. But then we realized that very universal could be not like the best approach because it's getting more and more expensive and you need more and more data. So then we went to this approach of problem-driven. So now we're just focusing on all the micrographies that have globular brain structures. So then we can just like have a more limited problem and better results. So now, just like a quick demo on how this works. This is a screenshot of a software that we developed at Clemex that is called Vision. So here we have an image, and here we have something that we call the routine window. Here we can put all the steps of the different things that we want to add to this image. And this is a toolbox. From here, you can have like different tools for like binary masks, all the classical vision tools. And we can also have some of the deep learning algorithms that we have developed. So you load your image, then you load the plugin that is called BrainSec. Here's a quick description. Different classes. Then once you run OK, then the prediction gets run in less than 5 seconds, and then you can get a predicted mask. So as you can see, this was a twin sample. You can have different shades of gray, you have inclusions, but the prediction is pretty well. Over the prediction, you can then run some different binary operations, for example, to remove all the brains that are in the boundary. And then you can just use another little routine to measure the ASTM number according to the standard. And then in this case, we have just one image, but here is the grain size number for the sample. But in case that you have multiple images from the same sample, you can get like the statistics and you can have relative accuracy or whatever is necessary. So this is how it works. Now let me tell you how good it is. In order to validate our algorithm, first we can do just like a super quick visual comparison. This is a ground truth. So we label a good amount of data. We really spend a good amount of money on that. And this is done by experts. Like all this is done by hand, so it can get very expensive, as I mentioned before. And this is like the prediction done by the model. So the first thing is just to do comparisons. Then we can also do like a more thorough comparison. So in this case, I'm showing each of these points is one file of my test data set. So these are probably alloys that were seen by the model, but that specific file was never seen by the model. So each point has an XY coordinate, and the X coordinate is the ground truth average grain size number. So we get the ground truth, we measure that was made by a human with a lot of care. We measure the grain size number, that is the X coordinate, and then we measure the same, but for the predicted is the average. Sorry, we measure the same for the predicted average grain size number for the same file. So if the ground truth grain size number and the predicted grain size number have exactly the same number, they're going to be over the identity line. That is this dark line. Now, in these areas, I marked a plus minus 1, plus minus 2, and plus minus 5. So as you can see, all the files for the different data sets that represent in different colors are over the identity line. That means that the model, for some of the cases, is like exactly the same prediction over the ground truth, or is plus minus 2. It's not bigger than that, which is like a pretty good result. Okay, so another way to validate it is like, as I explained before, we divided all the data in training, testing, and then we also select some amount of data that was never ever seen by the model. Over that data, I'm going to show you some of the different results. So for example, this is a twin sample. You can see here the perpendicular twins, like perpendicular to the grain boundary. And for some cases, you can even see that the twins are even like farther than the grain boundaries. This is the case from the testing data set. It means that the alloy was seen by the model, but the specific file wasn't. So for this case, we have like this is the mask predicted by the algorithm, and you can see that the algorithm ignored completely the twins, which is a good result. We have another case of under-edge samples. So here you can see that the grain boundaries are kind of like dotted lines. It's not like a very continuous line. We have also some twinning, some shades of gray, but the model like segment properly, the grain boundary is a little bit thick, but it's a continuous line. We have other cases like this one that is unseen, means that the model never saw this alloy before, but still is able to segment properly the grain boundary, ignoring all the porosities that you can find here. So, okay, maybe you're gonna say that I am cherry picking my samples and I'm showing you only the best, but what happens if you just give me one material, like the one that you have on hand? What happens if it doesn't work with greasing? Well, that's the beauty of having a foundational model because we can fine tune it. So this is an example. We have a client. As you can see now, this is an aluminum alloy, but the problem is that this one is polarized. So the way to segment this type of images is that the differences in colors are the ones that are going to mark a different grain boundary. So obviously, when we have the image and we pass it through the baseline grain set, we got a horrible result. But the good part of it is that with only 3 images, we were able to train this one. This is a fine-tuned prediction. And as you can see, yeah, there's like a little bit of like missing grain boundary over here and some extra lines, but it's a pretty good result, such that the client was very happy with it. So this is the beauty of having a foundational model that you can fine-tune it without too much data. So now I just showed you this that is only for globular grain microstructures. But Julian now is going to talk about what is happening in other niche cases.
All right, so thank you, Beth. So what about other niche cases? Maybe you want to analyze other kind of material or just other kind of problems. Do it correctly. Yeah, all right. So what we've been developing at Clemex is a tool called Clemex Studio, which is web-based. And this tool is a no-code tool, so you don't have to be an expert in computer vision or to have extensive infrastructure in order to deploy and train your model. And over this tool, as you can see here, this is the homepage of a demo account that has multiple kind of sample that we tried it on. And the goal of this tool is really to democratize, AI for microscopy imaging in general. So this one currently has a super simple process, and this is what we've really worked hard to achieve. So we want to have a UX that is really streamlined and that you can just use without heavy knowledge and without having to be a computer science expert in order to do your model itself. So this tool, we have currently a random forest space model, and we have also the quick Clemex net deep learning model online available there that you can train on, so you can fine tune them. And we plan on deploying others like the grain sec that Bertha presented. So the first step is to import your data. So on this slide, we just upload your image. So in this case, it's an image that has some particle in it with a paper fiber that had like a uncalibrated color on the sample on the microscope. So in the second step, once you have your image, in this one, I've already annotated the image. So it's simple as using paint, and you just draw over the pixels that you want to assign a class to, and the classes you can choose. In this case, I just use foreground and background, but you can name them and you can add more. Encourage an iterative process. So you go back and forth, you click on the train button, and then it trains, and then you go back to the end. You get the prediction, and if the prediction is not up to your desire, because on the first time maybe like you will think that another pixel on the image is of the wrong class, right? So you can go back to the. I'll try to go back. No, it's theirs. No. Ah. This one? Okay. Oh no. All right. So you can go back and add more annotation and then do the training all over again until you're happy with the result on your training set. But then you can also build it right into the tool, go to the validation tab and test it on unseen images that you can also upload. So it's the same thing. So you get to this tab, you upload your unseen sample, and you can validate those results over there. And this whole tool have other useful tools such as the measurements one, or you can also like document your samples with the textual annotation and things like that. And the whole goal of this is to be able to download your plugin which contain the model and run it in Clemex Vision that Bertrand showed right before, enabling you to do in-depth analysis and get report out of your samples. So now I will let Hector again discuss the Clemex NetLight model.
So as Julian said, right now in the free tier, you can use a random forest that was created by Julian's team. It performs really well, but we're deploying right now something that performs a little bit better based on deep learning. So this model is called Clemex NetLight version 1. We call it light because this is a model that sacrifices a little bit of accuracy, but it tries to go faster at the expense of accuracy. So it's a general purpose segmentation model. We use micronet pre-trained encoders. And the way we do it is, as Julian said, we capture these partial annotations from the user and then train this model on the partialized annotations. The way we do that is we use a weighted categorical cross-entropy, and because the cross-entropy doesn't care about the topological information of these data and train on these masked inputs. As for grade set, we also use two optimizers in this case with different learning rates. So we use an optimizer for the pre-trained part with a lower learning rate and an optimizer. So in this case, the pre-trained part would be the encoders pre-training micronet. And then the encoder and the segmentation head are not pre-trained. So we use a different optimizer with a higher learning rate. In the future, we also plan on deploying live versions of some of the models we have, such as BrainSeg, for niche applications, because ClemexNet is a general purpose segmentation model, but then we will have deployments of models that were pre-trained or more niche cases. So when we were doing the research to determine the hyperparameters or like the way we should be doing ClemexNet, we created a data set of 14 sub-data sets, and I will be showing you results for 2 of these cases. On the left, you have an image from one of our clients. This is a soldering image. And on the right, as Julian have showed you already, this is a filter with particles. So the task on the left, it's important for us to identify mainly this part, which is the heat affected zone. And then we have other classes such as the background and 2 other different parts of the metal. On the right, we really just have background versus foreground. So the way we did this research, for us, it was important to partialize these full annotations such that we could emulate the way Studio is actually being used by our clients. So what we did was we started from these full annotations, and then iteratively and stochastically, we created squiggles on the data until we have 10% of the image annotated. Once we did that, we trained the model and we see how it performs in each of these niche cases. So the way it works is that for each niche case, we have 3 images. One is used as training. So 10% of one of them is used on training, and then the 2 other images are fully annotated, and then we check for the performance with the full ground truth. So as you can see, with only training with 1 partially annotated image and being tested on a previously unseen image, the prediction, of course, it can be a lot better. But at least for our client, which they were very interested in this heat affected area, we can see that the segmentation is good enough. And in the case of the filter, the segmentation is pretty good. I think that we just end up predicting slightly more bad particles here. So that's why you can see in the error map a little bit of errors. And what I do want to say is that on the left side, this one ran for 150 epochs and it lasted 5 minutes on a laptop GPU, whereas this one, it lasted almost 3 minutes in a laptop GPU. So this is to show you that we really are trying to democratize and to lower the bar to access deep learning for applications in material science and microscopy segmentation. So at the end of the day, if you remember anything from this presentation, we would love it to be one of these 4 points. So first of all, deep learning simplifies microscopy image analysis. We can create semantic segmentation models using smaller data sets for niche application based on foundational models that are being created by bigger corporations. We believe that the democratization of AI in material science can be done through user-friendly no-code tools such as Vision and Clemex Studio. And finally, something that we learned the hard way is that really model validation goes way beyond the lab. We need to build test sets with domain relevant real-world edge cases before we deploy these models, such that we can know how they actually perform in previously unseen cases. So if we spark your interest, if you became interested in any of the projects that we're doing, please send us an email to info@clemex.com. We collaborate extensively with academia, so yeah, we would love to hear from you. That's it. We'll be taking questions at this point.
So if I understand correctly, one of the first things that you showed was that even with domain experts, there's often a difference in the way they annotate. How do you get over that when you're creating your graph?
That is an excellent question. So the whole process is that we hired an annotator company and then we train them for a number of, so first within the team, we created an ontology of how to annotate this data. It's a little complicated because especially with optical microscopy, differentiating twins from grain boundaries, it can. What we did is we trained these annotators for a couple of hours. They did a couple of prompts. They show us the results and we guide them. So it's really an iterative process. For us, the way we try to do it is that when we do the revisions of the annotations from the annotator, we have a two-step review process. So one person does what we call R1, which is like an in-depth review. So we really go we go to town, we take like 5-10 minutes per image. And then a second reviewer, really, when I say second reviewer, it's me and Berta. So we're the ML team, so it's really me and Berta that we do it. So usually I would do like a first review and then Berta does the second, or Berta does the first review and I do the second. So what we do is just add as many people as we can and try to come up with agreements within the team.
I think we have a question.
Yes, my question is when we want to use to show some new problem, that's the one you have not had yet. So do we need to provide the training data to train the model? For example, let's say we want to measure the nanoparticle on some sample. So we need to take many photo and then we label where is the particle. And then we provide all of that the data to the platform so that it can use trace machine learning to adapt to our new data to get the new prediction.
So Clemex Studio, this tool, it enables you to start either from your image without labeling. You can do the labeling on the platform, or we have a feature that is in the making that enables you to also import your masks alongside with your image so that you can retrain already acquired mask and label in this tool. Does that answer your question?
And we don't expect full annotation, so the platform is created to partialize everything, such that you upload. So you have the annotate UI and then you have the validate UI. So in the annotate, you upload as many images as you want, and then on each image, you take the brush, you assign. Then once you're happy, you trade. And this trading this trading will create a model in the background, and then this model will be applied to all of your images. So yeah, does that answer your? But we don't expect you can start from raw images, from full annotations, from partial annotations, all the options. Yeah, and this is Clemex Studio. We have a free tier, so right now you can just go to studio.clemex.ai and you can play with it as much as you want.
So at this moment, it's free for tries.
So see, there is a free tier, so you can use it as many times as you want. If you want more of the advanced features, there is a paywall. And also, this is cloud-based. We have a version that's desktop in case data privacy is an issue for your development. But I believe that there's no free tier of the desktop version.
No, I don't think.
Okay, there's no. The one that's free is like the simpler. Most of this is free, but like if you want to use the more advanced models, those are behind paywall.
But there's a trial.
Yeah, and then there's a trial.
Please do interact, Jordi. Thank you. And then one had a question.
Page 20, on the slide 20, can you present the characterization of the data? Yeah, sorry, then it's 22. Yeah, so all your data is very much in a very narrow place that when I look at the slope of the data, it doesn't match the slope of that you're predicting. So, I mean, Are you cutting it in a way that,
Okay, so first, problem is that the ASTM is a standard that we use to measure the grain size number. So that is ASTM marks where are the beans to, like, for example, I don't know the numbers, I'm sorry about that, but let's say that if your particle measures between 7 micrometers to 13, then it's gonna be called a 14.0 ASTM grain size number. So we have to use the standard. So what we do is we measure the areas, then we transform those areas to these ASTM standardized numbers. And that's what we're applying here, the size number that is from the standard. That's why all of them get like super common here, because those are the most common grain size numbers.
But in this case, so a lot of the data sets that we use are data that we had in the company, and there's no metadata, and we didn't have a calibration factor. So the clumping, mostly the clumping that you see there is explained by the fact that we just use a calibration factor of 1 for the data. So then, as Berta said, like they look very clumped because we keep the full beans of the ASTM standard, but we only use a calibration factor of 1. So that's why it comes there. If we had actual calibration factors for these images, then you would see a more widespread.
Hope we are still on questions.
Very quick question. So you said you can label the data. What kind of labeling is that? Do you provide the surfaces, visualization angle, or what kind of labeling would that be? That's the first question. The second question is you said you would very much like to collaborate with academia. Most of us are from academia. What kind of collaborations you are looking for?
You go.
Sure. So let's do this. So the first ones that we do, the labeling is really just pixel labels. So it's just the area labeling. I don't think we provide any kind of support for bounding boxes at this moment.
No, we provide,
No.
well, we have like bounding boxes for documentation purpose,
Right.
but not yet used for training. Things like that.
We have some other features coming up, so we just deployed the measurement tool so that within the image you can do a lot of measurements. And we have a data browser coming up. So based on the segmentation, you can say like, oh, create a database of the red class, and then it will catalog and classify like whatever you find in that one. So on the side of the collaborations, I can tell you a little bit what we've done before. So we've worked with some groups at the Polytechnic and Concordia. Mostly it was about getting data from them, getting guidance. So for example, for the GrainSec, the first data augmentations that we decided was in conjunction with a group of Concordia. Some of the data sets that we got them from different groups at the FAS and the Polytechnic. So to us, these collaborations can take the form of, you know what, you provide us with data, we can give you like a trial for something, or like an extended trial, or we can scratch my back, I'll scratch yours kind of situation. But for us, it's really about domain expertise, especially in cases for metallography, because most of our clients are metallography. And data, like really the industry.
Related to any materials or?
So it's mostly optical microscopy images. For right now, we're mainly searching for globular grains, so materials that exhibit globular grains.
But also dendritic, like aluminum dendritics also.
Yeah, and we also have quite yeah, that's it. We also have other applications like we're developing some mesh filter applications, so segmentation for mesh filter, segmentation for particle identification, for example, in the context of medical device cleanliness. So those are the kind of projects that we're working with. Yeah.
All right, thank you very much. And then just allow us proceed to the next.